Alright, hi everyone. This is starting off looking at static rigid bodies, which is the next part of the mechanics course that we need to look at. Okay, so for a rigid body which is in static equilibrium, the following things are always true. So the first one is that the body is stationary, okay, so not moving. The second one is that the resultant force in any direction is zero. We've covered these pretty thoroughly so far. And the last one is that your resultant moment is zero, okay, so that means that your anti-clockwise equals your clockwise. Okay, and also remembering that your moment is the perpendicular distance from the force to your pivot. Okay, and that's really important for later on. Okay, really, really important. Okay, so the first example we're going to look at in this case is this one. So we have a uniform rod AB. It has a mass of 40 kilograms. So handy here, you should underline all the important stuff. Okay, so we know that the mass is 40 kilos, has a length of 10 meters, and it's resting with end A on a rough horizontal ground. That means that we have friction. Okay, the rod has a smooth peg A to C, a smooth peg P C, where A to C equals 8 meters, and that means that C to B is 2, which I've already put in there. Okay, the rod is in limiting equilibrium at an angle of 15 degrees to the horizontal. Again, that's already in there. So our information that we need to now put in is the forces that are acting within this system. So we have obviously halfway along, because we're told it's a uniform rod, so I should have said uniform as well. Okay, so halfway along, about 5 meter mark, we have a force going downwards of 10G. Okay, that's our weight force. We also have a force, a normal force, I'm going to call it RA, where the uniform rod meets the horizontal ground. We also have another normal force at C, another reaction force. So that's perpendicular to the peg because the peg is exerting a force back onto the rod again. And then lastly, we also have friction, which is, if you imagine this rod is wanting to slide along the ground there, so it's acting opposite to that movement along here, and that's F max, okay, equals R times your friction coefficient. Okay, so, and sorry, I should say that's RA, not RC, okay, just to be clear. All right, now the first part of this problem says we want to find the magnitude of the reaction at C. Okay, so for A, we're wanting to find RC. Now, we have a lot of variables in here. We don't know RA, we don't know the friction coefficient, we don't know RC. The only thing we do know is the 40G. So the way we're going to approach this is by using it, is by approaching it more of like a moments problem than like a forces problem. So if we resolve using moments and we take the moments around A, that means that we don't have to include this reaction force at A and the friction force. Because if we assume this is our pivot, then the only forces acting on the pivot are the ones which are at some distance from the pivot. Okay, so taking moments around A, okay, we have this 40G, which is going to be acting in a clockwise direction around A. So we've got 40G, okay, and it's at a distance of, it's halfway along that 40G, so it's a distance of 5 meters, okay, from the pivot. Now we haven't 100% finished that yet, okay, so I'm just going to leave that for the moment, and that's going to be equal to RC times by 8. Okay, now they're the two forces. Now they don't, we're not 100% finished. We are actually finished on this side, but we're not finished on this side because when you're looking at moments, you're looking at the perpendicular distance. Sorry, I'm going to use green instead, something contrasting. Okay, so if we can see the perpendicular distance, if we make a 90-degree angle there, that RC is at 90 degrees from A. Okay, so that is at a 90-degree angle. Okay, and our perpendicular distance is just that distance between the 90-degree angle and A, which is 8. Okay, so that's done, that's fine. Okay, now this 40G times 5, that is not at a 90-degree angle to A. So we need to find the perpendicular distance, so the distance from this force and the perpendicular. So we're actually going to be finding this distance along here, okay? We need to multiply it by that. So if we're looking at that, we've got an angle here of 15 degrees. Sorry, that's way too thick. Okay, we have an angle here of 15 degrees. We're wanting to find that distance there, so we're going to do 5, which is that along there. So that's 5 times by cos 15. Okay, because we're wanting to find that angle of our triangle, so I'll just draw it because I don't think I explained that too well. Here's your triangle. Okay, there's your 40G. Okay, there's 15. There's 5. Okay, because it's 5 meters halfway along the rod. So we do, and we're trying to find this side here. So we use, so that's hypotenuse, adjacent, 15. So we're going to do x equals 5 times cos 15. Okay, and that's how we end up with that in our equation. All right, so then we can solve for RC. So 40G times by cos 15 divided by 8. So RC equals 40G times by 5 times by cos 15 over 8. And so therefore RC equals to 236.65 newtons. Alright, so for the second half of the question, we're finding the coefficient of friction between the rod and the ground. Now, I just wanted to go into this a little bit more and just do a bit of an investigation about what's actually happening at C. Okay, so I've drawn this little diagram for C. So here's our rod, there's our 15-degree angle, there's our C there. Now, we are going to start off by doing this by resolving vertically and horizontally. But when we're resolving vertically and horizontally, we can see here we've got RA, which is purely vertical. We've got a weight force, which in this case is purely vertically if we're resolving vertically. We have RC, and RC is kind of almost looks like it's meant to be vertical because you've got that 90-degree angle there, but it does actually have a slight tilt to it if we're looking at the purely horizontal and vertical fields. Okay, so I've put this line down here so you can see that vertical line, and that would be going straight through RC to meet up with the horizontal. Okay, and I've kind of zoomed in a little bit here. So we've got our 15-degree angle, we have a 75-degree angle. Now we know that's 90 there, so that means we have a 15-degree angle. Here's our right angle triangle. We've got a 15-degree angle, which is like the remainder in between RC and our vertical line. Okay, and this is the triangle we're going to be using when we're resolving horizontally and vertically. So if we resolve, we'll start off by resolving vertically. Okay, so we have RA, which is vertical, okay, plus, now the vertical part of RC is RC, which is our hypotenuse, times by cos 15, because we want this vertical part here of our right angle triangle. Okay, we then have that's equal to 40G, because we know we're in equilibrium, we're not moving, so that's equal to our weight force of 40G. Okay, from here we can solve because we know RC is equal to 240 newtons, so we have RA equals 40G minus 240 times by cos 15. Okay, so RA is therefore equal to, what was it, 163.41 newtons. Okay, so that's our RA force here. From there, we can solve to then find our coefficient of friction. All right, because we know that if we then resolve horizontally, okay, we can look at this horizontal component of RC. I'll just get another color. So this one here, that horizontal component there. So we have RC times by sine 15 in this case, okay, is equal to, now our only other force acting in the opposite direction is F max, which is RA times by our coefficient of friction. Okay, we know RC is 240, so we've got 240 times by sine 15 equal to RA, which is 163 times our coefficient of friction. So that then is equal to, so I'm just going to quickly work it out, 240 times sine 15 divided by 163. Okay, so therefore coefficient of friction equals 0.37. There we go, that's it. Perfect. All right, so that's example 1 done. We will have a look at example